And happy Tuesday to everyone, and thank you for showing up for your learning again. Today we are looking at function notation. Function notation is a very key idea in this course. We are going to be using this throughout the course. If you are uncomfortable with this topic at the end of the day, you will not be uncomfortable with this topic at the end of the course. It's something this is going to be the water we breathe as fishes swimming in the sea of math. This is something we use all the time.
That's a great analogy.
Yeah, so I'm full of those.
I didn't know where you were going at first.
Yeah. Here is a type of question that we're going to be rewriting this year using function notation. We've all remember these types of examples from grade 9 or grade 10. The cell phone company charges per minute of call time and a flat fee. We know that's going to create a line. We know how to read our slope. We know how to read our initial value. We're going to create that equation for a line later using function notation. It's going to look a little bit different, but we're going to find that this function notation is going to make a lot of things easier for us. We are going to like it by the end of the course. So let's take a look. We do need to remember the distributive property, where if I have a number or a variable multiplied by a binomial, this is a b plus a c, I can't simplify that. If I want to multiply that in, I have to multiply a times b and a times c. So don't forget your distributive property. And also don't forget to collect like terms after you distribute. So here, if I have an apple plus $4 in these boxes, and I have 3 of those boxes, I would have 3 apples and $12. And then this box has an apple but only $2 in it. And I have 4 of those boxes. So from those boxes, I have 4 apples but $8. Together, I have 7 apples and $20 between these 7 boxes. So this is collecting like terms. Don't forget to do that. Yeah, I'm using the wrong version of the PPT. I don't have you doing a collect like terms worksheet, but there are some things in the Delta Math today to help you review these topics. Now, let's carry on function notation. Let's say you were a physicist and you were analyzing these 3 linear systems. All right, these 3 linear systems came from your research, they came from your data, and you wanted to talk about them in a report. All right. Do you see how it would be awkward because all of them look the same over here? It's like y equals this, and so when x equals this, what does y equal? People are like, well, for which line are you talking about? Are you talking about the green line, red line, or blue line? So then we might end up having to say something like, okay, if y equals 2x plus 5, that has a y value of 9 when x is 2. How would you indicate that? Okay, so here is our 2x plus 1. Now, how do we indicate that we're 2x plus 5? How do we indicate that we're talking about 2x plus 5 instead of 2x plus 1? It's really awkward. You could refer to it in this sentence here, but it's very wordy to do this. We could talk about its Y-intercept, but what if two functions share a Y-intercept? We could talk about colors. What if you're going to publish in black and white? There's lots of reasons why that's going to get awkward when our systems of equations start going past even one equation. Even with 2 things, y equals this, and then we have a different one, y equals that. It's already getting awkward. So it's better to use function notation to differentiate each function from one another.
Oh, that's what this is?
Yeah, this is function notation. We're going to now start calling functions instead of y equals. We're going to be labeling them in this way. Okay. So, for example, and I have this on your handout here, so you have a copy of it. The way we read this is f of x is equal to x plus 5. F of x. When you hear f of x, what that's saying is I have a function. It is a function of the variable x. And so I put my input down here inside a little bracket. This does not mean take f, the variable, and multiply it by x. That is not what we are showing. And in fact, I'll show you on the board the way I distinguish these 2 ideas. If I have like a multiplied by a bracket x, then that would be like this. That's equal to a times x. But if you see me write f of x, and I write this as a subscript, and you'll usually see this written a little bit smaller and a little bit cozy to that letter, which is big. This indicates this is a function. What function? Well, I'm going to indicate it over here. The function could be here 2x plus 5. So the way I read that is f is a function of x, or f of x is equal to 2 multiplied by x plus 5. That'll be a line, just like we've seen before, and it would be effectively the same thing as y equals 2x plus 5. They're the same. But when I write this way, now I could have multiple lines. And I can look at multiple lines on the same graph, and I can name them different letters. So you will find that g of x and h of x are going to be your next most common ones. But f of x is by far the most common because f stands for function. G is just the next letter in the alphabet. And so we'll say g of x is another function, and h of x. And then you might see I of x, but probably you're going to go to j of x or k to x. Yeah.
So basically, you would use f on, like you wouldn't use like a of x or something like that. Like,
You could have a of x, yeah, and actually we have one right here, a of r. Okay. So we can describe the area of a circle with this formula here. See, area is a function of radius, is the way I would read that. Okay, and that should make sense, right? The radius determines the area, so area is a function of radius. Okay, a is a function of r such that pi r squared equals the area. A of r equals pi r squared is how I would read that. That describes the area of circle based on a radius. Or v of e equals e to the 3. That describes the volume of a cube based on an edge length e. Okay, so if I have a sugar cube and the edge is e long, then its volume would be a function of that edge length. And I could find that by e cubed. And then d of t, this is distance and this is time. So we'll often use letters that make it easier to read. Distance is a function of time, or d of t is equal to 4.9 times t squared. That describes the distance traveled by a falling object after t seconds. You'll notice that would create a parabola. That would be a quadratic. Yeah, so these are all different examples of functions that we're going to see. So if we go back to linear relations, it's easy to refer to individual functions if they're labeled. Okay, so let's go back to that picture. Oops, I need to click here. Boop, 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 there. If we just named this f of x, g of x, and h of x, it's very clear now which one I'm talking about when I say something like h at 3 is equal to, well, so let's say this one, h at 3. If I call this one h of x, h at 3 would be 2 times 3 is 6 plus 5 is 11. H at 3 is equal to 11. And it becomes much clearer what I'm talking about when I start using function notation. Okay, so down here. So, if so, blah, 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 blah. Okay, so here. So now another thing that we're going to do with function notation is we can say if this is f of x, so we have f of x here is equal to 2x plus 5. If I want to know f at 2, what that's telling me to do is substitute 2 in for x for that function. So not only can I indicate which function I'm talking about, but I can also specify my input there. I can specify which value of x I want you to evaluate, just with a single notation. So f at 2 is equal to 9. Let's see why. If I put in 2 for x here, 2 times 2 is 4. 4 plus 5 is 9. So f at 2 is equal to 9. That is true. Okay? And in this case, the x and f of x, we just replace that by 2 to give f of 2. Anywhere in the function where the variable x appears, we put the value 2 in its place. That's useful if we have a quadratic that's like f of x is equal to ax squared plus bx plus c, a quadratic in standard form. When I substitute in the x, I need to substitute it in a couple places. I need to substitute it in for the x squared term and for the x term. Let's carry on. So we've talked about functions as machines before. I like to think of them as vending machines. Whatever input I put in, it goes into the machine. The function does stuff to it, and then it outputs the value of the function at that x. Okay? So if I input $1.25 into the vending machine and push H3, the vending machine does some calculations and determines that I want to eat chips. And its output is chips. Okay? It's not going to be a Kit Kat. It's not going to surprise me. It will only have one output per input because it's a function, because it passes vertical line test, because no x value is repeated. So let's take a look at some examples. And you have this example on your sheet, so I'm going to switch over to Document Cam, and we can do this one together. So let's let f of x equal this quadratic, x squared minus 5x plus 1. Let's determine f at 0, f at 3, and f at minus 2. So here's what we would write down. First, I would just go ahead and copy my function. F of x is equal to x squared, this pen is my favorite pen, minus 5x, and it is dying, plus 1. Okay, so now to do f at 0, I just write f at 0. 0, and I'm going to use a different pen because I'm not that stubborn, is equal to 0 squared. You can substitute into brackets, minus 5 times 0 plus 1. Notice that I just substituted the given value of x in all the x places. And then I evaluate. F at 0 is equal to 0 minus 0, because 5 times 0 is 0, plus 1. F at 0 is 1. Circle it, final answer. Okay. Now let's do another one. F at 3. F at 3 equals, substitute into brackets, 3 squared minus 5 times 3 plus 1. Now evaluate. Equals 9 minus 15 plus 1. Collect like terms. There, you just have to do some this is what? This is grade 2? Okay. Maybe this is grade 3. Okay, so 9 minus 15. Actually, no, we're going below a 0. That's probably grade 5. Okay, 9 minus 15 gives me negative 6, plus 1 is negative 5. So f of 3 is equal to negative 5. And here I might rewrite f at 3, and then I circle it. Final answer. Okay. And we're asked to do one more, f at negative 2. So let's do it. F at negative 2 is equal to, substitute into brackets, please. Notice that substituting into brackets there makes a difference. Okay, so then we'll carry on. Hi there. You're here to join us for the day?
Yes.
Congratulations. Great. It's a great group. Would you like to introduce yourself?
Yes, I'm Mr. Kenneth. I'm the construction teacher.
Oh, great.
Yeah.
Yeah.
So when do you need to leave?
I need to leave by 9:15, so I'll leave
Okay.
at the first break.
Okay.
So do you want to hang out here, or do you want to hang out in my office?
Sure, I've got a couple of things I need to look up on the computer. Where's your office?
My office is the last room down here on the left.
Okay, thank you.
Yeah, 237, I believe. Yeah. Okay, so then just evaluate. So this is equal to 4, because negative 2 times negative 2 is 4. Notice that the bracket makes a difference. Negative 5 times negative 2 is positive 10, and 1 is 1. So this is equal to 15. F at negative 2 is equal to 15. Circle it, final answer.
Do you always circle your answers?
I always do, because sometimes I just want you to get in the habit of doing that, because it makes your test easier to mark.
Okay.
If your test is easier to mark, that helps you. It helps me give you marks. If I also, it shows me that you know that, okay, that was what I was looking for. That you're not just like repeating steps and saying, I don't know, am I done? I'm not sure. I'm going to move on from that question.
Right.
So when I circle it, when I know that that is what I was looking for, that was my goal, then that's knowledge. Okay, so that's what I'm just emphasizing there with that habit. Okay, now let's do another one. Here, g of x at 3x minus 2. So we have g of x would be what kind of shape? What shape will g of x make? It's not going to draw Humpty Dumpty. Yeah? It's a line. Yeah, it's mx plus b, so it's going to be a line. All right? So I want to determine g at 2x plus 1. What? Mr. Jennings, you said we can just substitute in for x. Yeah, okay, well, let's do it. I'll show you what happens. Okay, if g of x, and remember, I'm going to rewrite my function, is equal to 3x minus 2, okay? And now I want to know g at 2x plus 1. Whoa! Okay, I'm just going to substitute in, and remember to substitute into brackets. 2x plus 1 minus 2. All right? Notice I just substituted in that crazy stuff they told me to substitute in for x. I just substituted that in for x. See, this was x, now it's 2x plus 1. Substitute into brackets, and it helps you avoid mistakes. So now I remember I got 3 of those because I have to have 3x, and x is now this wacky thing that's also made of x. And so I could call that 6x plus 3 minus 2 equals 6x plus 1. So circle it, final answer. Okay? And yes, I could rewrite g at 2x plus 1 there. It might be a little nicer. All right, next. What would g at a be? Anyone hazard a guess? G at a is equal to, what am I going to write here? Siraj?
3a minus 2.
3a minus 2. Yep. Circle it, final answer. Very straightforward. Okay, and then last one. I just substituted a in for x. Okay, I don't know why we have to do that, but that's what we have to do. That's what that notation tells me to do. Okay, now g at 1 is equal to 3 multiplied by 1 minus 2. This is equal to 3 minus 2. G at 1 is equal to 1. Circle it. Final answer. Okay. So that's how we use function notation to input values for your variable. Usually x, but not necessarily x. Like we saw, a is a function of radius. Okay, now we can also translate things into coordinate points, okay? So here we have a function. It's f of, I don't know what even the variable is, but we're going to say it's f of x, okay? And what I'm told is for the input 2, I have an output -1. So I already have a point. I'm going to translate that into a coordinate point. So that would be a coordinate point, input of -1, output of 2. How about this one? What kind of point am I going to have here? F at 0 is equal to 7. What's my point going to be?
Input of 7, output of 0?
No.
Oh, switch it?
Yeah. So this indicates my inputs. My x values go here. Cole?
Would be 0, 7.
0, 7. Yeah. Input 0, output 7. And this one, what is this going to give me? I have f at -4 is equal to 3. What's my point? Yeah. -4, 3. Okay?
Why is the first one then?
Ha 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 ha. What did I do? Did I ever mention that I have this bad habit of writing my y's and x's backwards? I have this bad habit. And I need to be careful. And today I am rushing because I know I have a big lesson to do. So here, this one is my input is here 2. My output is -1. I did that to test you, to see if you were paying attention.
That's
Apparently
what
you
threw
are
me
paying
off,
attention,
actually.
so that's very good. Thank you very much. Jared, do you need some handouts, or are there handouts on your desk? Okay. So here's a function notation and maximum and minimum. This is yours?
Yeah.
Okay. Oh, yes, okay. I should have an extra. Maybe my extras are here.
I thought you grabbed 2 to say.
Maybe I did, yeah. No, I didn't. Huh. Well, I printed 34. It should be enough. Wait. I can print another 4 in a moment. Okay. So let's carry on. Now, we can also determine things from a graph here. So let's take a look at this one. So yeah, you can have that one there. And if you don't mind, I'm going to use this for the lecture. I should have another one for you, but let me print another one. All right, carrying on. So we can also determine values of functions from graphs. So here is our function. I'll give you a hint. This is going to have an x to the 3 term because it has 2 turning points. But we don't need that information yet. What we need is the value of the function at -3. So how am I going to do that? How am I going to find the output of this function at -3?
Plot -3.
Sorry?
Go to -3 on the x.
Go to -3 on the x. 1, 2, 3.
And then go up.
Then go up until I find it. Okay? So there is f at -3 is this point here. So I had to go up 1, 2, 3. So the value is 3. Okay? So that's going to give me an output of 3 if my input is -3. X when f of x is equal to 0. So what is the value of x when the output of the function is 0?
Y is at 0?
Yeah, we want to know when y is 0, what's the input that gives us a 0? That's what this question is asking me. What x will give me f of x is equal to 0? Julie?
-5.
-5 is a very good answer. 1, 2, 3, 4, -5. So I just look at the function and I want to find the 0 value for the y, or where the output is 0, and then I'm locating the x value. So that would be -5. Cool. When f is at 2, what do I do? When f is at 2?
To x coordinate of 2.
So you just draw.
Go up.
What are you thinking, Cole? I want f at 2.
I have an idea. No.
Okay, so I'm looking at inputs of 2.
So go to the x.
Jackson?
Wouldn't it be over 2 up 2?
It's over 2, and then it happens to be up 2. So it's this point here. That's the point 2, 2. So the output is what I'm looking for there. So this is 2. Okay, great. And then x when f of x is 9.
It's 6.
Is it 6? Okay, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice I went up 9 on the y, and then I go over here. And then that allows me to count 1, 2, 3, 4, 5, 6. Very good. Very good. 6. Yeah. So that's reading a graph using function notation. Something that we're going to want to be able to do. We're going to do a lot of that type of practice throughout the course. That's going to become like a language to you that you just speak without thinking about how to do it. You need some practice to get there. So Delta Math and textbook questions. So now let's take a look. A cell phone company charges a monthly fee of $30 plus 2 cents per minute. Let's create a function C in terms of call time T. Okay? And then let's find the domain and range of that function. So we have here, if I were doing y equals mx plus b, what would my b be? What's my initial value in this situation? $30. So b is equal to $30. And what's my slope?
0.02.
Yeah, m is going to be equal to $0.02. Cool. And what's my x mean? If I had a let statement, let,
20 minutes.
yeah, x equal number of minutes. And what's y?
Y is equal.
The cost.
Is the total cost, yeah. So in fact, we're not going to use y equals mx plus b now. We're going to create a cost as a function of time is equal to the m 0.02 t plus 30. And that, my friends, is circle at final answer. Let's find the domain and range of the cost function. T, the domain is t is a set of numbers such that t is of the integers or reals. What do we think? Probably integers, yeah. I don't think they're going to charge you for the half minute. They probably charge you by the minute. Okay, let's go. T is of the integers, but we don't know. It's not specified here. It could be of the real numbers. I mean, this is 2021. We can get real granular with stuff because of information. Okay, T is of the integers. And what are some limitations on T? Could T be -7?
No, it can only be positive. It's not
Yeah.
greater than 0.
So 0 is less than or equal to T. And bracket, cost is a set of numbers such that cost is of the, probably, what?
I just have a question in the circled answer there.
Yeah?
It says 0.02 plus something 30.
Oh, that's T.
That's a T.
That's a T.
Oh,
That's the time.
Yeah.
Variable. So it's basically X.
That's a T. T for time, because I have T over here. Tells me T for time. Cost is of the reals, because we can have pennies and things. And cost, it's going to be 30 is less than or equal to the cost. Cost can't be below 30. Okay? And that's done final answer. And I'll put that up so that everyone can see. And then we will say, that's function notation. That's a wrap. So thank you again for showing up for your learning and learning the critical function notation today.